Good morning, students. Today we will discuss next topic, that is shift micro operation. As we have started the topic, that is micro operation, in the last lecture we have covered arithmetic operations and logical operations. Today we will discuss the topic, that is shift micro operation. So firstly, I will discuss what does it mean shift. Shift means to shift the bits of the register to the left or to the right by one bit. Or you can say shift is the serial transfer of data. It is the serial transfer of data to the left or to the right by one bit. Let us suppose we have a register. This is a register. In this register, we have data 0, 1, 0, 1. So if we want to shift these bits, we can shift these bits either to the left or to the right by one bit. If you shift these bits, suppose to the right, so this bit will go out from the register. So this bit is discarded, and this bit is shifted to here, and this bit is shifted to here, and this one is shifted to here. And at this place, at this position, we will insert 0. So after shifting to the right, the result will be 1, 0, 1, 0. So this is the shifting of the bits from left to right. So shift means to shift the bit. It is a serial transfer of data to either to the right or to the left. So shift micro operation, basically it is of three types. It is of three types. The first type is logical shift, and second is circular shift. Shift is of three types. First is logical shift, second is logical shift, circular shift, and third one is arithmetic shift. So these are the types of the shift micro operation. So let's firstly discuss what is logical shift. In logical shift, we have to transfer the bits either to the left or to the right. In logical shift, the bits are not circulate from one end to the another end. So let's discuss it with an example. Suppose this is a register, and here we have let's suppose we have a 4-bit register. Let's take an example of 4-bit register, and this is the positioning. This is the numbering of the register 0, 1, 2, and 3. 0, 1, 2, and 3. These are the numbering of the bits of the register. So let us suppose if we have data 0, 1, 0, 1. So this is the data that I want to shift either to the left or to the right. So if I will perform the logical shift right operation, this bit, the bit at position 0 is out from the register, or you can say this bit is discarded. This bit is discarded. So this one bit is shifted here, and this one is shifted here, and this one is shifted here, and at this place, at the position of 3, we will insert 0. We will insert 0. So the output of logical shift right, this is logical shift right, the output is 1, 0, 1, 0. So this is the output of the logical shift right. In logical shift right, we shift the bit to the right one bit. The bit at position 0, that is discarded, and bit at position 1 is shifted to the 0 position, and bit at position 2 is shifted to the 1 position, and bit at position 3 is shifted to the 2 position, and at the bit position of 3 we insert 0. So in this way you can shift the bit to the right in logical shift. Same in the logical shift left. For this we use the symbol SHL. SHL. SH means logical shift right. SHR. SHR means logical shift right. Suppose if we have this is a register R. So if we want to logical shift right, so we write like this: SHR R. This means shift the bits of register R to the right by 1 bit and store the result in register R. So this instruction means we have to shift the bits of register R to the right by 1 bit and store the result in the register R. So this is logical shift right. Now if we talk about logical shift left, now next we talk about logical shift left. Logical shift left. Again, let us suppose we have a register which is of 4 bits, 1, 2, and 3, and this is the numbering of the register. And now we want to shift the bits from right to left by 1 bit. So again, suppose we have data 1, 0, 0, 1. So now we have to shift the bit to the left. So this bit at position 3 is discarded, and this bit is shifted here, and this bit is shifted here, and this bit is shifted here, and we will insert 0 at bit position 0. So in logical shift left, the bit position at 0 is shifted to the position 1, and 1 bit position is shifted to the position 2, and so on. So the output of this shift is 0, 0, 1, 0. This bit is shifted here, this one is shifted here, this one is shifted here. At this place we insert 0. So this is the logical shift left. This is the logical shift left. So for this we have instruction SHR. Sorry, SHL. This means logical shift L. Suppose this is a register R. If I want to write the instruction for logical shift left, for that purpose I will write R SHL R. This instruction will shift the bits of register R to the left by 1 bit and store the result in register R. So logical shift, we have 2 instructions. The first one is SHR and second one is SHL. These are the symbols to represent logical shift right and logical shift left. SHR means logical shift right 1 bit, and SHL means logical shift to the left by 1 bit. So this is about logical shift. So next type is circular shift. Circular shift. It is also of 2 types. One is circular shift left. Circular shift left and circular shift right. So circular shift, that is of 2 types. One is circular shift left and second is circular shift right. Again, let us understand it with an example. Suppose we have a register R which is of 4-bit register. Suppose it is of 4-bit register. 0, 1, 2, and 3-bit position. And suppose we have data 0, 1, 0, 1. In circular shift, our data is not lost. Like in logical shift, our data is lost because the bit position 1 or last is discarded in the logical shift. But in case of circular shift, data is not lost and it circulates from one end to the other end. It rotates. In circular shift, data rotates from one end to the other end. Let us suppose if we want to perform circular shift left operation. So this means this bit is shifted here, and this one is shifted here, and this one is shifted here, and this bit is shifted here. So this means data circulates. Data circulates. And in circular shift, our data is not lost. So this bit is shifted here, and this one is shifted here, and this one is shifted here, and this one is shifted at bit position 0. So the output of this is, the output will be 1, 0, 1, 0. So this is the output of the circular shift left. Circular shift left. In this circular shift, the data is not lost. So this means data rotates from one end to the another end. So this is the circular shift left, and the symbol for circular shift left is CIL. CIL. CIL means circular shift left. So now the next step is circular shift right. So again, let us take an example. We have a register R. Here it is of 4-bit, and this is the numbering 0, 1, 2, and 3. And here we have data 0, 0, 1, 1, 0. So this is the data that I want to shift to the right by 1. To the right by 1. So in circular shift right, this bit is shifted here. Bit position 3, 3-bit position, 3-bit position bit is shifted at position 2, and 2-bit position is shifted at 1, and 1-bit position is shifted at 0, and 0 is shifted to the bit position 3. So this one is shifted here, and this one is shifted here, and this bit is shifted at here. So this is the circular shift right. So we shift the bits to the right by 1 bit. So what will be the output of this? The output is 1, 1, 0, 0. This is the output. This is the output of the circular shift right. This is the output. So the symbol for circular shift right is CIR. 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 CIR is the circular shift right. CIR is the circular shift right. So these are the two symbols for circular shift. CIL means circular shift left. CIR means circular shift right. Now, how to write these symbols with in symbolic form? In symbolic form. For this is the shift left. So I will write CILR and this. So this means R. This means shift the content of R register to the left by 1 bit and store the result in the register R. So if I write for the circular shift right, I will write CIR R. So this means circular shift. So this will shift the content of register R. This will shift the content of register R to the right by 1 bit and store the result in the register R. So this is the circular shift. This is the circular shift. Now the next third type is arithmetic shift, and it is important for exam point of view. Arithmetic shift is important for exam point of view. Third one is arithmetic shift. Again, it is of two types. One is arithmetic shift left, and second is arithmetic shift right. Left and arithmetic shift right. So this is it is of also it is of two types. One is arithmetic shift left, and arithmetic shift right. So let us again understand with an example. First, we discuss arithmetic shift. In arithmetic shift operation, in arithmetic shift operation, we use a sign bit. We use a sign bit. Suppose again we have a data. Suppose for example we have data 0 1 0 1 0 1 0 0 1. Suppose this is the data. In arithmetic sheet we have sign bit. We have sign bit which represents the sign of the data. Which represents the sign of the data. Sign means that the number is positive or negative. The number is positive or negative. Then how we do know that the number is positive or negative? For that purpose, the leftmost bit, this one is the leftmost bit. This is the rightmost bit. This is the rightmost bit, and this one is the leftmost bit. Leftmost bit tells the sign of the data. Leftmost bit tells the sign of the data that data is positive or negative. If leftmost bit is positive, if it is positive, if it is zero, if it is zero, this means the data is positive. This means the data is positive. The number is positive. This means the number is positive. If leftmost bit is equal to 1, if it is 1, this means uh, number is negative. This means number is negative. In arithmetic shift, we have a sign bit. We have a sign bit which tells the sign of the number that the number is positive or negative. If and this is by the last bit, that is the leftmost bit. Leftmost bit of the number tells us the sign of the number. If it is zero, if the leftmost bit is zero, this means the number is positive. If the leftmost bit is 1, this means the number is negative. So this is arithmetic shift. Now we will consider the case of arithmetic shift left or arithmetic shift right. So firstly we will discuss arithmetic shift right. Arithmetic shift arithmetic shift right. So firstly, we will discuss the case of arithmetic shift right. Arithmetic shift right. So again, let us consider an example. Suppose we have a register which is of any bit. Let us suppose, and these are the bit positions 0, 1, 2, and 3, and 4. Let us suppose 5 bits. Let us suppose we have 5 bits. So in arithmetic shift, as I told you, the last bit, the last um, leftmost bit is the sign bit. If it is 0, this means the number is positive. If the last bit is negative, 1, so this means it is negative. So remember one thing, the sign of the number should be same. The sign of the number always should be same after the shift operation. If the number is positive, suppose if the number is a positive, after shift it also should be positive. After performing shift operation, it's again positive. So this means if the number is negative, after performing the shift operation, it should be negative. So we cannot change the sign of the number after performing the operation. So we will take care of this point in the arithmetic shift right. So arithmetic shift right is the easy concept. In this, if we have a number, let us suppose we have number 0, 1, 1, 0, 1. So this means the leftmost bit is 1. So this means the number is negative. This means the number is negative. If we shift the bits to the right by 1 bit, what happens? This bit out of the register, so this is discarded. So this is discarded, and this bit is shifted this, and this is shifted here, and this one shifted here, and the last bit. So we have to take care that the last bit is 1. It should be 1 after performing the operation, shift operation to the right in case of arithmetic shift. In case of arithmetic shift right, the last bit, it remains unchanged and shifted to the next position. So this means that this bit is remain unchanged. This will become here, this will here, and also it move to the next position. So this means this bit is shifted here, this one shifted here, this one shifted here, and this one shifted here. So the output is 1, 1, 0, 1, 1. So this is the output of the arithmetic shift right. In this case, sign bit remain at its place and also move to the next position and also move to the right by 1 bit. By 1 bit. So this is the concept of the arithmetic shift right. So this is the concept of arithmetic shift right. Again, I am repeating arithmetic shift right. In arithmetic shift right, the bits are shifted to the right by 1 bit. The bit at position 0 is out of the register and it will be discarded, and bit at position 1 is shifted to the right at position 0, and bit at position 2 is shifted to the right by 1 bit, and bit at position 3 is shifted to the right at bit position 2, and the bit and the leftmost bit, or you can say last bit, is at its own place and also shifted to the right. So this means this will be unchanged. This will be remain unchanged. It is on its position and also move to the right. So this is the arithmetic shift right. So it is important. Arithmetic shift operation is important for the exam point of view. So this is the arithmetic shift right. This is arithmetic shift right. So the next is arithmetic shift left. arithmetic shift left. And the symbol for arithmetic shift right is ASHR. ASHR. ASHR means arithmetic shift right. If I want to perform, suppose this is a register R. If if I want to perform arithmetic operation on a register R, so I will write arithmetic shift and the result stored in this. So here SHR means arithmetic shift right. Perform arithmetic shift right operation on register R and store the result in the register R and store the result in the register R. So this is the arithmetic shift right. Now the second case is arithmetic shift left. This is a little bit tricky how to perform arithmetic shift left. Again, let us understand it with an example. Suppose we have a register. Let's take an 4-bit register. Let's take a 4-bit register. For example, 0, 1, 2, and 3. You will also write the numbering like this in journal: R0, R1, R n minus 2, and R n minus 1. For example, n is equal to 4. If n is equal to 4, n is equal to 0, R0. N is equal to 0, we represent it with R0. If n is equal to 1, it represents with R1. If n is equal to 2, we represent n minus 2. 4 minus 2 means 2. If n is equal to 3, means 4 minus 1, 3, bit number 3. This is the journal in journal number. And this is the numbering of the register. So here, arithmetic shift left. Arithmetic shift left means we have to shift the data. We have to shift the data to the left by 1 bit. As I told you, the leftmost bit. This is the leftmost bit, and it represents the leftmost bit. It represents the sign of the number. Sign of the number, that the number is positive or negative. That the number is positive or negative. If and also I have told you that sign should not be changed of the number. If it is positive, then after performing the shift operation, it again should be positive. If it is negative, then after performing the operation, shift operation, it again should be negative. So this means arithmetic shift left in journal. If we talk about in journal, this means this bit is shifted at this position, and this one is shifted at this position, and this one is shifted at this position, and this bit is discarded. If we talk in journal, and here we will insert 0. Suppose if we have data 1, 0, 1, 0. And listen carefully, this one, when you shift data, this bit is shifted to this position, and this bit is shifted to this position, and this bit is shifted to this position, and this will be discarded. This discard because it is out of the register. Now, and here we will insert 0. So when we perform arithmetic left shift, this bit is at this location, and this one is at this, and this one is at this, and this one is discarded. So, and here we will insert 0, and the output is 0, 1, 0, 1. But initially we have 0. This means the number is initially the number is positive. But the after performing the shift operation, the last bit is 1 and it becomes negative. The number becomes negative. So as I told you, if the number is positive, it should be positive after performing the operation. If it is negative, it, it is negative after performing the operation. But here the sign is changed, and this will not be happen, and this is not a correct answer. So for this purpose, so this condition, this situation, when signs change, when signs when signs change means 0 becomes 1 or 1 becomes 0. That is called overflow. That is called overflow. That is called overflow. Overflow means the leftmost bit change. Leftmost bit change. That is overflow. If for initially it is 0 and after performing the operation it becomes 1, it becomes 1. So this means number has been changed. So this is called overflow condition. What is the overflow condition? When the last two bits are not same. When the last two bits are not same, that is called overflow condition. Now, for to check the overflow condition, for that purpose we will use XOR gate. We use XOR gate and a flip flop, B flip flop, and flip flop that is called B flip flop. So here, in case of overflow, when the last bit is changed with another bit, then we need a sign reversal. For example, in this case, and originally our data is 0, 1, 0, 1. But after performing the operation, logical arithmetic shift left, the answer is 1, 0, 1, 0. So this means the last bit, the leftmost bit has been changed. So this means we need a sign reversal. We need a sign reversal. In sign reversal, we again change this bit with 0. Again change this bit with 0, because we should have to remain, if the number is positive, then we should have to remain that number should be positive. So that's why we use a sign reversal. That's why we use a sign reversal. So here, with last two bits, we use a XOR gate and a flip flop B. Whatever the output of this gate, that output is stored in V flip flop. That is stored in V flip flop. The XOR gate, if both the bits inputs same, if both the inputs same. For example, if this one 0 and this is also 0, this means the both inputs are same. Output will be false. Output will be false. So if both are 0, output is also 0, and B flip flop is equal to 0. If these are 1, 1, 1, so the inputs to the XOR gate is 1, 1, and the output is also 0. Output also false, and the V flip flop again it is 0. If both are changed, if the last bit is 1 and the second last bit is 0, here the inputs to the XOR gate is 0, 1. Here we have overflow. Here we have overflow because the last bit is 1 and the second last is 0. When we perform left shift and the last bit becomes 0, so the negative number is changed to the positive number. So the XOR gate, if you give the input to the XOR gate 0, 1 or 1, 0, it will give true. It will give true 1. It will give true. If V is equal to 1, it will give true. If V is equal to 1, this means overflow. If V is equal to 0, this means there is no need, there is no overflow. If V is equal to 0, this means there is no overflow. If V is equal to 1, this means there is overflow. Then the value of V is set by this XOR gate. If the input to the XOR gate, if the input to the XOR gate is of same bit, means 0, 0, 1, 1, 0, 0, 0, 0, or 1, 1, the output of the XOR gate is 0. The output of the XOR gate is 0. And if the output of this output of the XOR gate is stored in V flip-flop. So if V is equal to 0, then this means there is no overflow. So if these bits, if the input to the XOR gate is 1, 0 or 0, 1, then the output of XOR gate is true, means 1. If it is 1, if V is equal to 1, this means there is overflow. The meaning of overflow means the last two bits are of not same. Means one bit is 0 or one bit is 0 and another bit is 1. So in case when V is equal to 1, we need a sign reversal. We need a sign reversal. In for example, like in this case. In this case, let us suppose if we have data 1, when you shift the data, you will get we will check the overflow condition. If these two bits are not equal, this means the output of this XOR gate is 1, and this 1 is stored in V flip-flop. If V is equal to 1, this means there is overflow, and if there is overflow, we need a sign reversal. For example, the output of this is 1, 0, 1, 1. Initially, we have data 0, 1, 0, 1. When you shift the data to the right by 1 bit, we will have output 0, 1, 0, 1. Here, the sign of the number is changed. So we need sign reversal. And this last bit becomes again 0. We will perform sign reversal for the arithmetic shift left. So this is all about arithmetic shift left, and arithmetic shift left is very important for the exam point of view. In arithmetic, again I am repeating what is arithmetic shift left. Arithmetic shift left means shift the bit to the left by 1 bit. In this case, we have in arithmetic shift, the last bit is the sign bit. Leftmost bit is the sign bit. If it is 0, this means the number is positive. If it is 1, this means the number is negative. And if these two bits are same, then we no need of sign reversal. But if these two bits are different, then we need a sign reversal. Because as I told you, if the number is positive, it should be positive. Also, after performing the left operation. If it is negative, it should be negative after performing the operation. So this means the sign should be same. Sign should be same before or after the operation. If the number is positive, then number should be positive after the operation. If it is negative, then number is negative after performing the operation. So for if the last two bits are n-1 and are n-2 is not equal, if these two bits are not equal, then this means we need that situation is called overflow situation. That is called overflow situation. Overflow situation means these two bits are not equal. So how we check that these two bits are not equal? For that purpose, we have a XOR gate. If the input to the XOR gate is of same bit, means 0, 0, 1, 1, the output will be false. If the input to the XOR gate is of different bits, different input means 0, 1 or 1, 0, means the output is 1. If the V flip-flop is 0, when the V flip-flop 0, when both the inputs to the XOR gate is same, then XOR gate gives 0. So V is set to 0. This means there is no overflow. Means here if here, then here 0 is shifted here. So this means no sign. There is no change in number. Sign change in number. So but if it is 1 and it is 0, so this means the number is changing from positive to negative. So here the inputs to the XOR gate is of 1 0. Means this means inputs to the XOR gate. So this means the number is firstly number is positive and after performing operation it's negative and it will give 1 and the value of 1 set to 1. So if V is equal to 1, then there is overflow. If there is overflow, we need sign reversal. We again change the sign of the number to the original sign. So this is all about arithmetic shift left.